OCR Chemistry A, amino acids, amides and chirality. We will start with the structure of amino acids and move on to look at their reactions, and then one of the properties of most amino acids, which is chirality or optical isomerism. And then we'll finish this lesson with a different functional group, the amides. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. Starting with amino acids. Proteins are polymers formed from 20 different amino acid monomers. Those amino acids are known as alpha amino acids or as 2 amino acids. As indicated in the name, the amino acids contain an amine group and a carboxylic acid group. So the acid part is a carboxylic acid group, and the amino obviously refers to the amine group. If we look at the displayed formula for any alpha amino acid, we've got an R group here, and of course there are 20 different R groups. With a central carbon, a carboxyl group, an amine group and a hydrogen. That is the general formula or displayed formula for an amino acid. Before we go on, just pause for a moment and explain why is it they are also known as 2 amino acids. Come back to me when you have your answer. Okay, so if we think of the carbon chain, this would be carbon number 1, this would be carbon number 2, and whatever is in ways of carbons in the R group. But the amino group is always located on carbon number 2 because carbon number 1 of the carbon of the carboxyl group is always designated as carbon number 1. So carbon number 2 has the amino group attached to it, so they are 2 amino acids. If this is the displayed formula, you'll also see amino acids represented as a structural formula. Could you write what you believe to be the structural formula for any amino acid? So use the R group. What is the general structural formula for an amino acid? Pause, think it through, produce your answer, come back and check. Okay, so here I'm going to reveal. So here's our R group, CH, then NH2 is a substituent. So that, because it's amino, it's not the main functional group, so it's a substituent, so it's in a bracket. So RCH NH2, and then carbon number 1 is at the end of the chain as we write it left to right, so COOH. So R on the left, COOH, the carboxyl group on the right, and then CH and NH2 within a bracket, it's bonded to the previous carbon. So I'd like to give you 3 problems based on the structure of amino acids. So the R group is hydrogen, alternatively CH3, alternatively CH2OH. Can you draw the structure of the amino acid and deduce the systematic name. Pause the lesson, attempt structure number 1 and its systematic name. If you need help, you can move forward through the models that I provide. Come back when you have thought it through and had a go. Okay, so if we look at the first structure, we'll see that the R group is hydrogen. So we've got the absolute structure, general structure of an amino acid. Carbon number 2 is bonded to the amino group or the amine group. Carbon number 1 is a carboxyl. We have a hydrogen of carbon number 2. And then the R group, I'm highlighting there, is hydrogen. So if we then replace hydrogen with CH3, we keep exactly the same structure for the amino acid, except we change hydrogen with a methyl group, and then exactly the same structure for the amino acid, but the R group is CH2OH. Let's look at the names. I'm going to reveal the first name. So we can see, if we can explain 2-aminoethanoic acid, I need to identify the longest carbon chain. It starts at the carboxyl group, so that's carbon number 1, carbon number 2. So 2 carbons explains the ethanoic acid, and on the second carbon we have an amino group, so that explains the 2-aminoethanoic acid. If we now look at 2-aminopropanoic acid, so I'm identifying the longest carbon chain with the carboxyl group at carbon number 1. So it's a 3-carbon chain, so that explains propanoic acid. And on the second carbon, of course, there is an amino group. So if we look at the third example, again, we need to identify the longest carbon chain. So starting with a carboxyl group, the longest carbon chain is of 3, so it's going to be named as a propanoic acid. On the second carbon there's an amine group, so 2-amino, but on the third carbon there is a hydroxyl, so it's 2-amino, 3-hydroxy propanoic acid. Amino acids are generally referred to by their common names, so at least an awareness of some simple examples would be helpful, although these are not on the OCR A specification. Glycine, the R group is H. Substitute CH3 for the H atom, we have alanine. Those are the 2 simplest amino acids. A more complex amino acid in that it has an additional functional group, serine. So amino acids are generally referred to by common names, although these are not in the Chemistry OCR A specification. The reactions of amino acids. So let's discuss the Bronsted-Lowry acid-base properties of amino acids. Now, as we saw in the structures, amino acids all contain an amine group, and of course an amine is a proton acceptor. So if we look at that as an equation, here's an amine, NH2 attached to some other molecular structure, accepts a proton, the hydrogen ion. Can you complete the formula of the product? Pause, complete, come back to check. Okay, so here is the product. Of course, the nitrogen has a lone pair of electrons that can form a dative covalent bond with the hydrogen ion, and therefore we refer to that as a protonated amine. So the amine group is protonated. We balance for charge, of course. The carboxylic acid group, always present in an amino acid, is a proton donor. That is the Bronsted-Lowry definition of an acid. So here's a carboxylic acid, carboxyl group, and any other molecular structure. We need something to donate a proton to, water in this case. Can you complete the product side of that equation? Pause the lesson, come back to check your answer. Okay, so if I reveal, the proton is lost from the carboxyl group and is gained by, or accepted, I should say, by the water molecule to form the hydroxonium ion H3O+. We are left with the carboxylate ion. Okay, so let's look at some real examples of reactions between acids and amino acids. Now, amino acids, the acid-base properties of the amine group are retained, and the acid-base properties of the carboxyl group are retained. So the reaction with hydrochloric acid does not involve the carboxyl group, only the basic amine group. So pause the lesson and suggest or write the formula of the products of this reaction. Okay, so I'm going to reveal. The amine group is protonated. So the acid, hydrochloric acid, will donate a proton. The amine group of the amino acid will accept a proton to form the ammonium salt. Do not forget to balance the equation with the chloride ion. So let's move on to reactions with bases. Again, if we take an alkali like sodium hydroxide, the amine group will not be involved, but the carboxyl group will show its acid property by reaction with sodium hydroxide. So pause the lesson and complete the equation with the product formulae. Okay, I'm going to reveal. Make sure you're ready. Okay, so the hydrogen from the carboxyl group, the acidic hydrogen, is lost and reacts with hydroxide ion to form water, and we are left with the sodium salt formed by the carboxyl group. So our amino acid shows both basic properties by reaction of the amine group and acidic properties by reaction of the carboxyl group. One interesting consequence of the acid-base properties of the amino acids is an internal transfer of protons to form what's called the Zwitter ion. So the Zwitter ion is produced by the carboxyl group deprotonating and the amine group protonating internally. So a carboxylate ion is formed and the ammonium ion is formed, and those coexist. Of course, the positive and negative cancel out, so the Zwitter ion has no overall charge, but the internal charges explain the crystalline nature of solid amino acids. This is not listed on the OCR A specification, but has appeared in a lot of past paper questions and is relevant to those of you who are studying biology. Let's move on to another reaction of the carboxyl group, which is esterification. Now I hope you will recall that carboxylic acids esterify with alcohols in acidic conditions. So if I present a general structure of a carboxylic acid and a particular alcohol, ethanol, and represent the acidic conditions with a H plus in the equation. Now I'd like you to pause the lesson, maybe look back at notes or think it through carefully. What is the organic product of the reaction between this general amino acid and ethanol? I will assist you to some extent by saying one of the products is water. Could you identify the main organic product? Pause, come back when you are ready to look at the model. Okay, so I'm going to reveal. Here is our organic product, and of course we have water. Where does the water come from? Well, we are eliminating water in a condensation reaction. So water is eliminated. And we are forming an ester. So here is our ester. But please note, the amine group is protonated. We are in an acidic environment. We are in acidic conditions. So our end product will not be the amine, but the protonated amine, the ammonium salt. And you will see that that therefore explains why we need H plus in the equation, otherwise the equation will not balance. So OCR A expects you both to know about the esterification, the loss of water, but also the protonation of the amine group in acidic conditions. Next, we want to talk about chirality, also known as optical isomerism. Before we discuss chirality, optical isomerism, an overview of isomerism so far at A level is probably advisable. So we have met so far in isomerism structural isomerism, of which there are 3 strands. Pause and think through what types of structural isomerism have you met, and perhaps some examples. Come back when you are ready to discuss. Okay, so there are 3 types. Skeletal. So for instance, we might have, simplest example, butane and methyl propane, different carbon skeletons. We might have functional group isomerism, for instance, aldehydes and ketones, propanol and propanone. And we might have positional, propan-1-ol, propan-2-ol. So structural isomerism is characterized by the same molecular formula but different structural formulas. Now in year 1 you will have also met stereoisomerism. Pause the lesson and write down what do stereoisomers have in common, but how also do they differ. Pause, come back when you are ready. Okay, so the stereoisomerism you have met is EZ and a special case cis-trans. Now EZ isomers have the same molecular formula, the same structural formula, but differ in their 3-dimensional relationship in space, their spatial arrangement. EZ and cis-trans are the examples you have met in relation to the chemistry, in particular, of the alkenes. But we're now going to introduce optical isomerism, or otherwise known as chirality, as a second form of stereoisomerism. So again, stereoisomers have the same structural formulas, the same molecular formulas, but a different relationship in three-dimensional space. Chirality is shown by carbon atoms which are surrounded by 4 different groups that are bonded to 4 different groups. So we can represent that in a simplistic way with different colours representing different groups. So red, yellow, green, blue, or type 1, type 2, type 3, type 4. Central carbon. Obviously we have a tetrahedral geometry around the carbon. We've got 4 bond pairs which will repel to form a tetrahedral arrangement. But the key to determining chirality is to identify or to draw structures that have 4 different groups around a central carbon atom. So if we start with the central carbon surrounded by 4 different groups arranged tetrahedrally, the chiral isomer, the enantiomer, will be the mirror image of that structure. So pause the lesson using this line as the plane of a mirror. Draw to the right the mirror image of the structure to the left. Come back when you have your best effort. Okay, so I'm going to reveal. Here is my best effort. It's not perfect, but my best effort at a mirror image. You'll notice the distances from the plane of the mirror are retained, but also the direction of the bond. So this bond is going behind the screen, this bond is coming out in front. These two are in the plane of the screen, and similarly on the left-hand version. But there's so enantiomers, that is chiral isomers, are mirror images of each other. They are formed by molecules which have a central carbon surrounded by 4 different groups. But one more thing, they are non-superimposable. By that I mean, if I attempt to pick up the molecule on the left and impose it on top of the molecule on the right, you will see that the two things are not identical in 3-dimensional space. They are like your left and your right hand. So I'm going to pick this up, try and place it on top of the other molecule. You'll see that there's a mismatch between the green and the red. So this is the key line. The chiral isomers, the isomers are non-superimposable mirror images of each other. So we've got, to recap, a carbon surrounded by 4 different groups arranged tetrahedrally in 3-dimensional space. If we draw a mirror image, those mirror images are not the same although they have the same molecular and structural formula, they have a different relationship between the groups in 3-dimensional space. And that is shown by trying that we cannot impose one image, one structure upon the other. So they are described as non-superimposable mirror images of each other. And the carbon, which is bonded to 4 different groups, is known as a chiral center. And that is often denoted in diagrams, questions, etc. with an asterisk. So a quick review of 3D representation with a view to scoring all the marks in an OCR A exam. The first thing is that the bonds that are on the plane of the screen or on the plane of your piece of paper keep a consistent width. So the bond CD and the bond CE are both on the plane of my screen. The bond that starts off thinner and gets wider is coming out of the screen towards the viewer. The bond that starts off wider and gets thinner, that is a bond that is going behind the screen away from the viewer. That format must be followed. In addition, OCR is very hot that this bond, this angle here, is not 90. So it must be greater than 90. Similarly, don't draw this bond here at about 5 o'clock as part of a continuance of the bond CD. So that would be wrong. We require the bond to be off at an angle. So this bond here must not be 90, and this bond here this bond angle here between C and D and imaginary position for B must not be 180. We must show some way of representing the triangular base of a tetrahedron. So if we look to the right without my squiggles, that is what the exam board is looking for. Usually about 2 marks. But any right angles, any bond angles of 180, lack of clarity over bonds getting thicker or wider or bonds getting thinner, any lack of clarity will cost you 1 if not both of those marks. So you need some practice. Identifying a chiral center. Which of these 2 molecules shows chirality? And identify the chiral center in that particular case. So 2-chlorobutane and ethanol, which of those shows chirality and where is the chiral center? Pause, attempt to answer that question, drawing structures, come back to look at my models. Okay, so I'm going to reveal, first of all, I'm going to start with the structures. So here is 2-chlorobutane, CH3, CH2, CHCCl, CH3, ethanol, CH3, CH2, OH. So if I draw the structures out, that may be helpful. So here's my carbon, here's my CH3, CH2, carbon, hydrogen, carbon, chlorine, and then CH3, we can see straight away that we do in fact have a carbon which is bonded to 4 different groups. Ethyl group, chlorine, hydrogen, and methyl group. I'll just slightly correct my writing there, that's meant to be a 3. Whereas ethanol, CH3, bear with me, if I draw that structure out, you can see there isn't a carbon with 4 different groups attached. So chlorobutane is going to show chirality, and the chiral center will be as I have placed the asterisk. So let's apply chirality to amino acids, which is why the exam board have included it in this topic. Which of glycine and alanine exhibits chirality? Look back in your notes. If you don't recall, glycine and alanine, common names for the 2 simplest amino acids. Which of those 2 exhibits chirality? You'll need to draw structures. Pause the lesson, come back when you are ready to look at the models. Okay, so I'm going to reveal glycine. The R group is a hydrogen, so you'll see the central carbon is bonded to 2 hydrogens and therefore cannot be bonded to 4 different groups. It does not exhibit chirality. If we look at alanine, the central carbon is bonded to a hydrogen, an amine group, a carboxyl group, and the CH3 group, which is the R group in alanine. So yes, alanine will exhibit chirality. It has a central carbon atom bonded to 4 different groups. In that case, draw 3D structures of the chiral isomers of alanine. Pause, spend some time drawing accurate diagrams, 3-dimensional diagrams of the enantiomers of alanine. Come back when you are ready to look at my versions. Okay, so here are my 2 chiral isomers enantiomers. We've got a carbon, 4 different groups, CH3 mirrored, H mirrored, the bond is mirrored, bond going behind the screen to NH2, bond going behind the screen to NH2, bond coming towards the viewer, carboxyl group, bond coming towards the viewer, carboxyl group. Not absolutely necessary, but it sort of emphasizes the mirroring if you do COOH on one side and COOH on the other, so the order of atoms is mirrored as well. It makes the point. So let's move on. So the last section in this lesson is the properties and structures of the amides. So let's look at the structures of this new functional group, the amides. Just as with amines, with which amides are often confused, there are primary, secondary and tertiary amides. So here's an example of a primary amide. The key point is that the nitrogen here is bonded to 1 carbon, so there's just the 1 nitrogen carbon bond. Alternatively, you can count the hydrogens. There's 2 hydrogens, but most usually we say this is a primary amide as there is just the 1 nitrogen carbon single bond. Please note the distinction between an amide and an amine. The amides are NH2 group linked, covalently bonded to a carbonyl group. So we've got carbon oxygen double bond, carbon single bond nitrogen. That is the amide group. Do not confuse that with amines. This is commonly done. So take a mental note now. Amides have a carbonyl group directly bonded to the nitrogen. Now what would be the name of the amide? Well, I'll give you an example. So this is propan amide, propanamide. So 1, 2, 3 carbons, which explains the propan, and then we've got the functional group amide, so propanamide. In which case, here are 2 more examples of amides. Would you like to name those? Pause the lesson, think it through, come back to check your answers. Okay, so I'm going to reveal 2-methyl butanamide. So I'm looking at starting, this is carbon number 1, 2, 3, 4. There's my longest chain with 4 carbons. So that's butanamide. We don't need to number because butanamide must be on the end of the carbon chain. So the amide group must be on the end of the carbon chain. So butanamide, which means we need to position the methyl group as a substituent, so 2-methyl butanamide. If you haven't already done so, have a go at the right-hand molecule. I'm about to reveal 2-amino propanamide. So I'm identifying the longest carbon chain. On the second carbon we have an NH2, an amine group, which we name as a substituent as an amino. So 2-amino propanamide. So let's look at secondary amides. In fact, OCR A doesn't require knowledge of tertiary, so I'm going to limit it to secondary. Let's start with naming secondary amides, looking at an example. Here is a secondary amide. Hopefully it's clear why it's a secondary amide. The nitrogen is directly bonded to 2 carbons via single covalent bonds. So nitrogen single bond carbon, nitrogen single bond carbon. It's an amide because the nitrogen is directly bonded to a carbon of the carbonyl group, so that is a secondary amide. Now we have an N naming system, so this is N-methyl propanamide, so I'm identifying the amide and the longest carbon chain, so that is the propanamide part. There is propanamide. But we've got to position this methyl group. Well, it's directly bonded to the nitrogen, so we indicate its position. It is located on the nitrogen, so N-methyl. So N-methyl propanamide. So identify the longest carbon chain attached to the amide functional group, so propanamide. And then, we've got in a secondary amide, we've got a methyl group to position. It's located on the nitrogen, so N-methyl propanamide. In which case, name these two. Name these two. Pause, come back when you are ready to correct or check your answers. Okay, so I'm going to reveal the first. There's N-ethyl propanamide, so I'm identifying propanamide, the amide group, and the longest carbon chain, including the carbon of the carbonyl. So there's propanamide, and attached to the nitrogen is an ethyl group, so N-ethyl propanamide. What about the one on the right? Pause if you haven't already done so and name it. Come back when you are ready. So I'm going to reveal. So this is N-methyl butanamide. I've orientated my amide in a different direction, which the examiner is quite entitled to do. So here is the amide functional group and incorporating the longest carbon chain. So 2, 3, 4. So this is butanamide within the green circle, and attached to the nitrogen, which I've deliberately placed at an odd angle, is a methyl group. So that's N-methyl butanamide. So let's look at how to make primary and secondary amides. Now, this is actually listed in the reactions of acyl chlorides in the specification. However, it's a good opportunity to revisit and to make links. So it is indeed a reaction of an acyl chloride with ammonia that makes a primary amide. So for example, ethanoyl chloride and ammonia would make a thanamide, with hydrogen chloride, HCl, being eliminated in a condensation reaction. Would you like to draw the structures for that equation? Pause, take your time, come back when you are ready to check. Okay, so if I go through that, so ethanoyl chloride, there is ethanoyl chloride, obviously ammonia. The key point about ammonia is that it has a lone pair of electrons, and that is going to attack the electron deficient carbon of the carbonyl. So what are the products? Ethanamide. So the carbonyl is retained, but the chlorine is eliminated as part of the hydrogen chloride molecule, and there is our ethanamide. Okay, so what about making a secondary amide? If this is the structures involved in making a primary amide, such as ethanamide, you can react a primary amine with an acyl chloride to make a secondary amide. For instance, ethanoyl chloride and methylamine, a simple example. What would be the structures and names of the products? Pause and come back when you have drawn structures and named the products. Okay, I'm going to reveal. I hope you've done your work. So ethanoyl chloride and methylamine will make N-methyl ethanamide. What do those structures look like? Well, ethanoyl chloride again. There is ethanoyl chloride. Methylamine. Again, it's the lone pair on the nitrogen that will lead the reaction mechanism, not required on OCR A. All we need is the product. Careful not to overload the nitrogen with bonds. It's got a maximum of 3 bonds unless it is the ammonium ion. And of course, HCl. So we have methyl ethanamide and HCl, which is eliminated in a condensation reaction. So let's have a look at the role that amides play in proteins. So amino acids polymerize, as I hope you realize, to form proteins, but what holds the amino acids together is called in biology the peptide link, but is in fact better known as an amide link. So if we simplify matters, rather than looking at proteins, which of course are thousands, hundreds and possibly thousands of amino acids, we can just look at linking 2 amino acids together to make what's called a dipeptide. This will bring out the chemistry. So if we look at an amino acid, so I've got my central carbon, my carboxyl group is carbon number 1, carbon number 2 has an amine group, and I've orientated it so that the amine group is to the right and the acid group is to the left. The R group, which can be one of 20 if you recall, and the hydrogen all come off the second carbon, so it's a 2 amino acid or an alpha amino acid. Now if I pair that with another amino acid, we'll see, you can see why I have set it out as it is, because it brings into proximity in my diagram the hydrogen from an amine and the hydroxyl group from the carboxyl part of the amino acid. I'd like you to draw the structure of the dipeptide formed by a condensation reaction with the loss of water. So pause the lesson and draw the dipeptide that is formed by the combination of these 2 amino acid structures with the loss of a water molecule. Come back to check your answer when you're ready. Okay, so I'm going to reveal. So Water molecule is lost, so I've highlighted those in a blue colour so you can keep track of where they've come from. And that means that the nitrogen here bonds directly to the carbon of the carbonyl. So the nitrogen bonds directly to the carbon of the carbonyl. And this, of course, is now a secondary amide. So the nitrogen is bonded to 2 carbons, so that's a secondary amide. So the dipeptide is linked together by an amide group, amide link, amide bonding. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.